Alright, part 3 of 2.1.4, and hopefully the last part to this section. Starting with question 11, we have an I screw that is experiencing two tension forces. Question 11 says sketch vector G with its x and y components. So let's go ahead and do that. We have a 5 point here. We've got our first vector is our y vector. That's G in the y direction. And then our second component is G in the x direction. So we have our component form of vector G, and then the second half says solve for component forces. So when I look at this, I'm breaking that into two components. Over 15 we have Gx, Gy, which is what I have drawn over here on the left. To find Gx, if we did sine of 15 degrees and cosine so we're looking for G of x. We're going to solve this fraction, or this equation. The fraction has G of x on top, so to get G of x by itself, we just find that we take 100 times sine of 15. And we get, I think it's 46.98, but again, we have a precision restriction right here of 1 unit past the decimal. So we get 47.0 newtons. Again, we had 46.98, but that does not follow our precision rule, so we rounded up. Rewriting the equation that has G of y in it, getting Gy by itself, we found this to be 17.1 newtons. So you could rewrite that as make sure I said that right. Wow, my numbers are very off here. I apologize. I was looking at the following answer for H. That is components for H. So let's, that's why we do all this in pencil, right? I always say that. So I'm doing it in pen, but I can erase it. So again, get those erasers out. Erase your answers for Gx and Gy. The reason I knew those were wrong actually is if you look at the component G sub y, that is a much longer component than G sub x. And what I was finding in those two answers I had written previously was that Gx was greater than Gy. So something wasn't right. I was tipped off just by the fact that my vector arrows did not represent the same lengths as the magnitudes I was getting. So let's go back to that. G of x should be smaller, and it turns out to be 25.9 newtons. And G of y should be 96.6 newtons. There we go, that's better. And making all sorts of mistakes here. There we go. So 11 is solved. 12, you're doing the same thing, except your vector is now got a much longer x component. So we have h in the x direction and h in the y direction. So if I drew that as a free body diagram, sometimes you draw in the final resultant vector h, or whatever letter it is. Sometimes you don't, but this time I just chose to draw them differently, g and x, where this one I showed the resultant vector. So again, with this one I'm going to do sine of 20 degrees takes our opposite, which is h of x, over the hypotenuse, which is the magnitude 50. And cosine takes our adjacent side h of y over hypotenuse 50. So again, solving for h of x, we get 50 times the sine of 20 degrees, and that is 46.98. But we have to round to our precision of 1/10 of a unit, and h sub y, solving for the h sub y, we get 50 times cosine of 20 degrees, and that is 17.1 newtons. So again, 17 smaller than 47, my y component vector should be smaller than the h, and it is. So we've just solved number 12, just like we did for 11. We drew our free body diagram vector in component form, and then we used our sine of 20 degrees, cosine of 20 degrees to solve for the component forces h of x and h of y. In 13, they're asking us to sum the forces in the x direction, and we will do the and the y direction. We'll do the x direction first. So in the x direction, our g force in the x direction, we found 25.9. And that again is positive. And we just found h of x to be 47. So the sum of the forces in the x direction should be 72.9 newtons. Box that in. Some of the forces in the y direction are g in the y direction is 96.6. And h in the y direction was 17.1. So the grand total sum of forces in the y direction come out to be 113.7 newtons. There's question 13. Question 13 is just calculate the sum total of the x's and of the y's. Question 14 says if you know the components of a vector, what mathematical relationship can be used? That is, simply put, abbreviated, the Pythagorean theorem. So, we don't have our vector here, so just let me pause the video for a moment. So I've now got that sketch in. I don't know why it wasn't there before. So, sketching the resultant force, this is the opposite of everything we've done to this point, which is instead of being given the magnitude of the resultant force and finding x and y, here we're being given the x and given the y, so we need to use Pythagorean's theorem to solve for what is the actual resultant force rather than the components. So we're going to say a squared plus b squared equals c squared. In this case, let's call that 114 squared plus plus 73 squared is our resultant force squared. So to get r by itself, I'm going to move that to the left side. I'm just rewriting it. And I'm going to take the square root of both sides. and we get, in our calculators, if you run the numbers, if you wanted labels, that's newtons squared. So our resultant force is 135 newtons up and to the right. Now the theta is, so if we did tangent theta equals opposite over adjacent, we find opposite of that is our r sub y, 114 divided by 73. In order to find theta, we do tangent inverse of this fraction, 114 over 73, and we find theta to be 57.4 degrees. From there, that's all it asked for, was calculate the magnitude, done, 135 newtons, and the angle of the vector to the nearest tenth. So, yeah, 57.4 degrees. So we're done with 1 through 15. Our conclusion questions, you and someone else are pulling at different directions on a sled, but you're each pulling at the same angle. How could you reduce the amount of force? Well, here's what's happening is some of your, whatever, let's say this is 100 pounds or 100 newtons, doesn't matter. If you each pull 100 newtons, the problem is you're 100 newtons this way. The amount of force pulling the sled up your hill or along the sidewalk, wherever you're pulling your sled, whatever force you're putting in 100 pounds isn't all going directly into the motion of the sled. So these cancel out. Your AY and BY, those cancel each other out. So all of the effort that you're putting in, AY, BY, is going to nothing because they sum to 0. So how could you reduce the amount of force you each exert? Well, if you reduce the angle. So if you reduce the angle at which you are exerting this, more of your effort, more of the 100 pounds is going to go towards your x direction, which is where you, in the end, are looking to get that sled to move, is in the x direction. Conclusion question 2, you and someone else are pulling in an object of 50 and 75. So if you're allowed to pull in any direction, what range is possible? Well, if you're each pulling this box, the range would include, let's say you both pull exactly opposite of each other. That would be the maximum of your range. The other end of your spectrum, the other end of your range of magnitude, is if you both pull in the same direction. So you have magnitude where they're opposite each other, and the magnitude of when they pull together. So that's conclusion questions 1 and 2. Find the actual values. I do want you to find the values of putting these magnitudes in these two orientations, away from each other and in the same direction. But that is it. That is the rest of 2.1.4.